Okay, I think we can start. Any question about the previous session? Just one thing about my office now that was overlapping with she, because he first set his time, so I need to change it. My time will be, previously it was 1 p.m. to 2 p.m. Now it is 1:30 to 2:30, the same place and the same day. Wednesday, room number 207, cube number 1. I will also announce it in the canvas too. So let's get started with autoregressive modeling. One point that I think was to some extent misunderstood in the previous session, truly 2 points. The first point was that we see that how chain rule can factorize the distribution for us. Because I cannot write bold letters, I put an underline for vectors. The distribution for a vector x is the distribution over the first, the distribution over the second given the first, till the end. The distribution over the last given the previous ones. Okay? But for this part, for this term, we need 2 parameters for, one parameter. For this term, we need 2 parameters till then. But the most important point is that for the last term, we need 2 to the power of v minus 1 parameters, assuming that the length is d. I made a mistake. Sometimes I take this d instead. I use n, but I want to focus on the d because I will use it throughout the course. To characterize, for example, one of those distributions, assume that I am talking about xi given the previous one. What do I need? I need a table. What is that table? That table have all possible combination of these terms in the condition. It means that x1, x2 through xi minus 1. And for all possible value for the whole vector, for this whole vector, you should give me a lambda, which is the probability of the resulting distribution, the resulting Bernoulli distribution. So if I want to fill this table, I need, how many combinations do they have, assuming that they are binary? 2 to the power of I minus 1. So for each row, you need a parameter, a different lambda. So the total number of parameters here is 2 to the power of I minus 1. This is a huge number when I go, when I is for a real world application, not for a simple. But instead, what do? We say that you can take a combination of the value for these conditions using a affine transformation. We call it, I think, Wi vector transpose with x less than I, we show it here this way, plus a bias term. Independent of the value in the condition, you apply this rule and generate your parameter for your Bernoulli distribution. So your number of parameters changes from 2 to the power of I minus 1 to I. because you have I minus 1 parameters here and 1 parameter here, totally I parameter. This really simplifies. You know, for the small values of I, they may not have very different, but for the large values, they are completely different because this is linear, this is exponential. Okay, this is the first note. The second one, how about, we just talked about a very simple case where you have binary random variables. What happens if you do not have, you have categorical random variables? For example, for the first one, let's focus on the density estimation task. Assume that instead of a binary variable, which is here, this x1 is a categorical, the categorical random variable with, let's say, C different categories. What happened? What should we change? In this procedure, we just need one number because the 0 or 1. It is the probability of 1, and 1 minus this value is the probability of 0. So what we just need one parameter. We need the probability for 1 for 0, but the summation is equal to 1, so we need 1. What happened here? How many value do I need to characterize this different cases in the general case?
C minus 1.
Exactly, C minus 1. So instead of a scalar B, assume that I have a vector B, 1. So this vector can be an arbitrary vector. And an arbitrary vector cannot be the parameter of a categorical distribution. What should I do? Exactly. The softmax can make it suitable for us. So just we change this scalar to a vector with the dimension C, and then switch the sigmoid into a sigma, softmax. I have the distribution over x1, and each element in this vector showed, for example, the first element showed the probability of x1 equal to 1, until the last element will show the probability of x1 equal to C. Okay? What about the second? Assume that we are now estimating the probability, the density over this random variable. Again, I do not need one number here. I need C, a vector of length B here. Okay? What should I do? Instead of having a scalar W, I should change it into a matrix such that here I have a vector of dimension C, and the bias is also C dimensional, and as a result I have a softmax, and here I generate the parameter of the distribution over x2. So everything will be updated accordingly, so we can have density estimation for a categorical random variable. For example, for the real MNIST data set where each pixel is in between 0 and 255. Okay? Any question about these 2 points? So we are ready to start the generation. Similar to previous density estimation task, now we want to generate samples using a given model. We do not focus on how the model is trained. Just assume that these values are given to you. How do you generate sample from the model that these parameters characterize or model? So let's start for the generation of the first element. Why we generate the first element? Because of our factorization of the density. Because we characterize the density, we factorize the density using a chain rule. We have access to each conditional distribution over isolated random variable. So I use the same procedure to generate samples. What do? I have the model, so I have access to this V1, It is summed with nothing because it's the first element, and then it goes through a sigmoid function. It generates a lambda 1. This lambda 1 is the parameter for this distribution. So to generate sample of x1, it is just needed to sample from this distribution. This is a Bernoulli distribution, and in the first session or maybe the second session, you see how to sample from a Bernoulli distribution with a known parameter. So I can sample from this and generate x1, x bar 1. So the first element of our generation is done. So what do I do next? I put this x bar 1 into the vector because it is generated now. And how I want to use this element to generate the distribution over the second element, I need this first one. So I use the x bar 1. The x bar 1 is used in exactly the same procedure as density estimation to generate the parameter for the distribution, and then a sampler samples from that distribution and it is called x bar 2. Pay attention that it is not an independent sample generated independent of x1, because x1 is working in the procedure of determining the parameter for the density. So x1 bar, your previous generation is playing a critical role here. Okay? So x bar 2 is generated, then you replace it in the input, and until the end. At the end, you weight all the elements you previously generated, excluding the last one that you do not generate yet, and create and calculate this parameter for a new Bernoulli distribution. And using the sampler, you can sample the last element and put it here. This is a generated sample from your distribution. Any question about the procedure we generate samples?
Can you go over it very quickly?
Yes, sure. You know, to generate samples from this type of distribution, because the way I characterize the distribution is by isolating each element condition on the previous in a predefined sequence. We know that you should assume a sequence. The last one is D given the previous ones. I can easily write the previous one as this one. So you know that the distribution over x1 is conditioned on nothing. So, and you have the parameter for this distribution because the model is given to you. Okay. So, what is the distribution for the first element? We know that the distribution for the first element is a Bernoulli over the first random variable given the parameter. The parameter is here. The parameter is the lambda 1. So you want one sample from this distribution, you can easily generate. You generate it and name it x bar 1. This is your generated sample. To calculate the distribution over the second element, because you have access, you need to x1 to be given, you replace it with generated sample. You have a generated sample. You have also a procedure to design to calculate the parameter for this distribution. So the resulting is the Bernoulli of x2 given lambda 2. You know that the lambda 2 is a function of x bar 1, and consequently, you can generate sample from this distribution, and you call it x bar 2. Sorry, I made a mistake about the notation sometimes. Okay. So x bar 2 is generated. X bar 1, x bar 2 are simultaneously used to characterize the distribution over the third element. You have both of them. You have the model. You can calculate the lambda 3. You can generate x bar 3. and go to the end. Okay?
Quick question. So, not in the generation, but in the training, we found all the parameters, for example, P of D, given all the kind of parameters before, right?
But you mean by parameters the model parameter?
Yes.
The learning is to some extent different. In the learning you are given the samples. It means that you are given, for example, we see that maybe this section that we see how to train them. Training them is just as easy as calculating the density estimation. It's just as easy as the same.
I'm a little bit confused on the generation and training. It seems to be
No, they are different. They are completely separated. Assume that you are given a model. You are given a model. The model is trained. You have the best value for V1, V2, for W1, W2, any of the parameter, and then you just need to generate sample from that model. You have a model which is characterized, and someone else have previously learned it. Yeah.
So just to reiterate, you use all the basically vectors on the learning, and then we take generate from the samples of the generation.
Yeah. You have a data set. You are given a data set. For example, the data set of MNIST images. You use them to train your model or equivalently design this parameter for the best value for these parameters, and then you are generating new samples. And definitely they are not exactly similar to your training. This is our objective. You train it over MNIST, and then you can generate new samples from MNIST. Yeah, you can see some samples from generation in the next slides.
So lambda 3 is x2 bar and x1 bar.
Lambda 3 is a function of x2 bar and x1. You can see that we have a vector W3. The first element of W3 is multiplied by x1 bar, and the second element of W3 is multiplied by x2, and then they are summed, and then a bias term, we call it B3, is added, and then a sigmoid, and then the output is the lambda 3.
Oh, okay.
Yeah, you cannot see it here. Here we just write for the second. The third is not written, but the last one is written. You can see that the WD, the vector to characterize the last element, the first element, the second element, until the D minus 1 element. We know that WD is of the dimension D minus 1. It is multiplied with each of these elements, or equivalently a vector, which we call X less than D is inner product with WD. It means that this relation, and a bias term, then a sigmoid. This is the parameter for the last distribution, for the last element. Okay? Yes?
But does density estimation also assume trained model?
Yes, exactly. Both of the tasks, we now just want to characterize the family, which family we are working with. Then we see that all the autoregressive model can be easily trained, very easily trained. It means in the sense of understanding. In the practical aspect, we might have some problems. Okay? This is the generation. This is just a notation of the generation. It means that, assume that we have a function. This function is the parameter calculator. Given, for example, the parameter for the diff element, we know that the first element is generated using independent of other element, because it is not conditioned on anything. So you have a model over the first element. This model is fixed. After the model is trained, this is a Bernoulli of x1 given lambda 1, and you can generate sample. Then for the next one, you calculate this lambda d function given the generated samples. You see, these are the generated samples, and they are given to this lambda 2 function, and the lambda 2 function generate the parameter for the second element of the vector, and then you can generate it. You can go to the end, and at the end you have a complete generated sample. This is a complete generated sample. So fully visible Sigmoid belief networks are very, very simple. Compare them with binary logistic regression, for example. Binary logistic regression, it was the simplest model for supervised learning. This is also one of the simplest model for generative modeling. As you can see here, these are the samples from Caltech 101. The data set is not binarized, but in this paper, you can see the paper here. In this paper, they use the binarized version of the data set and train a model over these figures. The resulting generated samples are these samples, and as you can see, based compared to the complexity of a model, which is very low, the generated samples are to some extent similar to the true data set samples. And they are not exactly the same as each other. Maybe you have sometimes see some similar samples, but you generally see innovations in your generated samples. Okay, this is the first results we see of generated models. We do not know how to train a model yet, but we will see that the training is very understandable and easy. We want to continue with family characterization. We do not talk about how to learn a model yet. So the next model is neural autoregressive density estimation, which is abbreviatedly called NADE. It is a very well-known model in generative modeling. So what is the main limitation of BLR? Binary logistic regression or multinomial logistic regression, they have a severe limitation. What is that limitation? What do you think? Assume that, let me talk about the data set. Assume that I have this data set. Think of supervised learning. This is my data set. It is yes.
You can only understand linearly complex, I guess.
Exactly. The limitation is that they can just provide you with linear margins, with linear decision boundaries. So you cannot extend them to the cases like this. This case is not linearly separable, so if you try to train a BLR over this model, although the BLR is the loss function for BLR is convex, but you cannot find a model that can discriminate both class perfectly. So what can we do? How we fade this limitation in the supervised learning world? Yes?
You can introduce an linearity term.
Exactly. Deep learning in the context of supervised learning exactly do the same. It transforms your data into a model, into a board, where in that board the data is really linearly separable, and then the last layer, which is usually a softmax layer, can perfectly discriminate them. It means that this way is deep, for example, learning. We can say it, for example, representation ring, something like that. We transform the representation from the original word to a transformed word, and in the transformed word, we assume that these are separable, and then we add a softmax layer at the end of our network, and that layer can separate both classes. Now we want to exactly apply those techniques here to fully visible sigmoid belief networks. Because fully visible sigmoid belief networks assume that by using an affine transformation and going through a sigmoid or softmax, you can generate the probability. Now assume that the connection is not as simple as we think. So we can extend our model with this way. So let me check what we have in this slide. So this is the BLR model, and the most important point, the limitation is that the line which generates the half probability is a linear line, so you cannot do anything more than linear separation and linear separable problems. So we can use this technique. Instead of using x here itself, we can use a transformation of x, which we call it h of x here. H is also another vector. So h is the feature transformation function. This is the case that I talk about here. You see that in the original world, the samples are not separated using a linear. But if you apply a very simple transformation like this, you you transfer into this world where the samples are linearly separable. In this world, assuming that this is your original data set, you can use a BLR to generate this line. And then if you transform the line into the original world, you can see that it is, for example, a circle. Okay. This is just the technique that we want to extend fully visible into NADE. Again, the chain rule, we do not have nothing more than chain rule in Autoregressive. Yes?
So, how do we decide how to transform the data set from, you have done that from x1, x2 to x1 squared, x2 squared, right?
Yeah.
So how do we do that?
How do you apply it, for example, in supervised learning?
No, which function to use? We square the input, right? There.
Yeah.
So
I said that I assume that we are in supervised learning. How do I design this H?
Yeah.
How? I apply a network. I give the H a network and, for example, parameterize the function using some variables, I say alpha. And then using the data, I learn this alpha. Here is exactly the same. We introduce some new variables, parameter, and then optimize them to have a better generative model. Yeah. Exactly the same. Okay. So, what is my concept here? Here again, previously I see that, for example, for p of xi given x less than I, what do I do? I said that this is a Bernoulli of x, random variable xi, and the parameter is generated using this way. X less than I plus bi. This is exactly what we had before. And now, instead of this x less than I, we want to use a hidden representation. And that hidden representation is generated using this formula. You talk about how we generate, we characterize the transformation with a WD and a CD. These two are the parameters that generate the representation for you. And as you can see, I should select a dimension for my new hidden space. What is the dimension in that hidden space? I select the edge as the dimension for that hidden space. So, irrespective of what is the position of the sequence, previously, for example, for the ith element, I have I minus 1, a feature of I length I minus 1 here. For example, it is dependent on the sequence position. But here, independent of the position, you have a feature HD, and HD is always of the dimension DH. How? You see here. For example, again, assume that I am in the same position as, I think I have a great figure of this procedure also. Let me talk about in this manner. I want to show you how I can density estimate in NADE, and then you can easily understand how the parameters are generated. Again, for the first element, we have nothing except a bias. Why? Because you do not have any input, and your input is empty now. So the feature transformation is not applied for the first element. But for the second, what happened for the second element? For the second element, I just have access to x1 as the condition. So I put it in a vector. We know that is a scalar, but for the sake of generality, assume that it's a vector. This vector is x less than 2, which have just x1. So it is in the dimension of r1 times 1. Also, I generate a vector. It is a parameter, you know. It is the new parameter I introduced for generating the hidden representation. This vector have just one column, and the dimension of that column is dh times 1. So what happened next? I multiply this vector, this matrix in the general case, with this vector dh times 1 times 1 times 1, generate a dh times 1. So the result of wx, w dot x less than 2, is a vector of dimension dh. And then I add, this is the red notation is related to the parameters. The C2 is again a new parameter which I added for my hidden representation. dh times 1 plus dh times 1 generate a new dh times 1 vector. And this h2 is the things that I fed to calculate the parameter for the Bernoulli distribution. Again, the input is transformed into h, and then h is here instead of x itself. This is just adding some flexibility to the model. The model have new parameter w2, c2, and these, then you can see that these can be generated to maximize the likelihood of your dataset, which means that you have a better generative model. This is just for one element. Go to the next one. This is from here. It is exactly as previous. We see that the representation should be inner product with a new vector, and then a bias is added, and I forget to add a sigmoid here. But the bias, when the bias is added, it goes through a sigmoid and then generate the parameter for the second element, lambda 2. We see previously that how I can generate lambda 1, and now how I can generate lambda 2. So for the general case, for the general case of estimating lambda d, for example, assume that I am in the dth position. So what I have to condition on, I have x1 through xd minus 1. Why? Because I am in the step d, and in the step d you can be conditioned on all previous steps. Okay. So I have a vector of dimension d minus 1 times 1 here, okay? On the other hand, I have a matrix. This matrix should be such that it can be multiplied with this element. In other words, if you are familiar with some types of matrix vector multiplication, as I mentioned here, assume that this is your vector, this is your matrix, your parameter matrix, and this is the vector that should be multiplied with. So what happened here? You easily weight that the result of this matrix vector multiplication is the result of this multiplication is that you should multiply this vector using this element, then the second with the second column with the second element, and the last column with the last element. They are multiplied, and then all of them are summed together to generate a new vector. and this vector is of dimension dh times 1. Because each of them is dh, you multiply them with the corresponding element in this vector, and then sum them together, then the result is a vector of dh times 1. Okay. So as we go further and further, the dimension of this matrix is increasing. For the first one, you can see it has just one column. For the second one, for the second one, it has just one column. For the second one, because it has just one element here, it has one column. For the third, it has two. For the d, it has d minus one column. Here we have the elements. They can be multiplied together. You can see the dimension. This dimension can be multiplied by this dimension. You multiply them together. Again, you have a vector of dh times 1 here. Then you add a bias term, which is cd here, and the result is hd, your new representation here. What do you do next? In the next, dh is exactly the input here. It should be multiplied by a new vector, which we call vd, and then added a bias term, and and the result is a scalar. That scalar goes through a sigmoid here, which I do not show here, and then generate the lambda d. Okay. Any question? If you have some, if you cannot follow this procedure, let me know so I can talk it further. Yes?
So, if the model is trained and we have all the weights, while generation at the inference time, only one of the samples can be created with the set of weights that have been trained. How do we generate multiple samples with the same set of weights?
You mean generating new samples using this model?
So once we train, there is only one set of weights that we have, right?
Yeah. We are not generating something now. We just we want to say how a model, a NADE model, can be used to density estimate. Next, we talk about the generation, how we can generate samples. Yeah.
Okay.
We want just to characterize the family. You know, in the next session, you will see that we want just to see how. Assume that this is NADE. Can you talk about fully visible sigmoid belief network in this environment? Where is fully visible sigmoid belief network? Exactly, it is inside this. Why? Fully visible belief sigmoid network. Maybe the right description. Why? Because in a special case, you can convert NADE into a fully visible sigmoid belief network. I think I made a mistake here. So we just expand the family, hopefully in an intelligent way, hopefully. Okay? Why do we talk about the density estimation of this model? Because the learning is just density estimation, nothing more. We will see that to train this model or learn this model, you just need to density estimate for some data, which are your training data. Yeah, nothing more. Yeah, it is as easy as density estimation. The concept, I mean, but the optimization may be some trick. Yes.
Oh, what does DH mean again?
You should select a dimension for your hidden space. You know, for example, in a deep learning also, you should select the dimension for the hidden space. DH is because we just have one layer here, just one layer, because this is the layer. Exactly these two operations together are the layer, because in each layer, for example, a fully connected layer, you just have a matrix vector multiplication plus a bias term. This is exactly a layer. So I should select a dimension for that layer and that DH. Yeah. Yes?
What is C and what is B?
Yeah, C and because to be aligned with the paper, I use W and W here. But VD is our previous W.
Okay, so wait.
Yeah, exactly. Our previous W, because it was applied on a vector and a bias was added, and the result was generate the parameter for your model. Because to be aligned with the paper, I use this notation. Maybe it was better to use V instead of W. Yeah.
H is what was previously X.
Exactly. H is what was previously X with a minor difference. You know why? Previously, X was, for example, when you go through your samples. For example, for the D samples, X was X less than D. You remember? Was here. For example, in the D element, X was of dimension D minus 1. For 2, X less than 2, it was of dimension 1. But here, for all the elements in the sequence, the dimension of H is DH. It's fixed. It is maybe a preferred. Yes?
Do we have any problems like this in the homework at all?
What?
Problems like this in the homework at all?
You know, the homeworks are to some extent the extrapolation of what we talk here.
I see, okay.
Yeah.
Not the specific, but I understand. It's like is there like something to practice on, you know?
Yeah, the basic concepts are here because the TAs were aware of the presentation and they design based on the presentation. I hope. Okay, yes.
So here X is a single image with 3 dimensions, right?
Yes.
So let's say we have a data set of 10 images.
Yes.
How do we generalize it over 10 images?
You know, here I just estimate the density. You are given a model, and you instead of one sample, someone can give you 10 images. I can sequentially start to estimate the density for each of your images. The task here is just assign one number, which is the probability, to each of the image you give me. I have the model, okay? I have the trained model. You give me several samples. I should give you a probability for each of those samples.
Okay, so like, let's say 10 images belong to 10 different classes.
We are not talking about classes here. We are generating. We do not have any label here. Just the concept of extending BLR was used here to generate the distribution over the sequence of input elements. We do not have any label here. Yeah.
So we calculate like separate lambda value for each image.
Yeah. You know, we will see some, I think, it was not soon. We'll see some samples. You know, assume that I train NADE over MNIST, okay? I have NADE over MNIST. From now on, if you give me a sample and ask me if your sample is exactly the same dimension as MNIST, and ask me whether it is a valid digit image, I can give it to you, my NADE, and calculate the probability for your image using this procedure and give you an estimate. You can, based on experience, can design that. For example, if the probability is less than a number, it means that that image is not a digit image. Maybe it is a valid image of something else, but it is not a valid image from the distribution that MNIST digits are coming from. Okay?
So in that case, we need to have like different probability distributions for every digit.
Yes. Each image you give me, I'll give you a new number. Yeah. Because some images are coming from MNIST, some of them are, for example, image of face, and the image of face have low probability in the model trained on MNIST.
For example, like in MNIST, there are like different digits, 1, 2, 3.
Yes.
So for them, like every pixel will have different probability distribution for every digit.
Yeah.
And
you multiply them together. The multiplication, the result of multiplication is the probability of that image. Because this type of modeling is based on sequential modeling. The probability of the first element, the probability of second given first, third, and till that. Okay? Yes.
What is C?
C? C is a parameter for your newly added layer. We added a transformation layer, and that transformation layer also have a bias. In addition to your previous bias, which is a scalar, you are given a new bias, which is a vector. It is a bias added to each element of the representation, your hidden representation. You know, it means that you have more flexibility for the representation you are learning. Yeah.
It's calculated or?
No, all the red parts are trained.
Okay.
Yeah, all the red parts are parameters, and they must be trained during your training procedure, and we can see that how you can train it. Okay, any question? Okay, let's go.
Last question.
Yes, sir.
I'm looking at the presentation. There is no.
Oh yeah. One important point is that something that I send you in the Canvas may be different from this, but now this presentation is on Canvas.
Okay.
Yeah, I updated because maybe I find because this is the first version, and I may find some errors inside. For example, these images are not, I think, added in the presentation you have in Canvas. All of them are new. Yeah. Okay. Any question? Okay, let's move on. One important point is that here you see that for the first element we have nothing, just a bias. Let's talk here. For the first element we have nothing, just a bias, and the bias was enough to calculate the parameter of the output of that element. But for the second one, we need a vector, a column vector of DH, and also C, V, and B, which is nothing. For the next one, assume that I want to calculate lambda 3. How many columns does this matrix have? Exactly. It has 2 columns. I can generate totally different 2 columns for this matrix. But for the purpose of more generalizability, we can share parameter here. What do? I take the first column from the previous one. It is fixed. It is they are the same. It means they are the same. And just add a new vector, a new column vector of dimension dh times 1. And then again, these are the other parameters. You see how they act. One more important point is that instead of C1, C2, and C3, I have C. Again, the bias is also shared. Because the bias is for all of them is dh times 1. So I can assign one dh times 1 vector and call it C, and use it for bias for all of the sequence position. Okay? For the fourth, I have 3 columns, but 2 of them can be shared from the previous one. So I put 2 of them from the previous and add another new column to my matrix. And again, C, which is similar to the previous ones, but it has its own V and B. They are not shared. And until the end, for the second last, you see that we have D minus 2 vectors here. And you know that these D minus 2 vectors, all of them are shared from the previous layers except the last one. And these are the other parameters. And finally, we have a matrix of dimension. This is a problem with the figure. This is dh times d minus 1. This is dh times d minus 1, and these are the other parameters. So you see that. I just need this vector, and having access to this vector, I can generate all of these W matrices. Okay, excuse me, this is a matrix. I just need this matrix, and having the access to this matrix, I can generate all of these matrices. So the parameters are shared, and the generation is better in the case that you have a limited number of samples.
Can you mention the C part again for this one?
Yeah. You mean the parameter sharing? How it is done?
You said something about C being the same for every.
Oh yes. You know, in the previous part, if you see here, we have CD, for example, here, CD, C lowercase d here. It means that it is different. C2 here, and C1, we do not have C1 because the first element is not dependent on anything. You know, these are different. But we can share both this matrix and this bias term, bias vector, so that we can have a better generalizable model in the case that you have access to limited number of samples.
So on this diagram, where does weight sharing happen?
Here I do not assume weight sharing. I talk about the general case. You know, they have a superscript D. This means that it is dedicated to WT. But here I just add W. Yeah, W1, W2, and it does not have any superscript, so it is shared. The first one was the general case. This is the shared case. Okay. So I can share the parameters, and this makes the problem a bit simpler. You can see that this parameter sharing is used in different models, generative model. Any question about parameter sharing?
Why do we need it? Where is it used?
It is to some extent used, for example, when the data set is limited, because it limits the flexibility of your model, because a model without parameter sharing is more flexible. We can talk about the diagram again. If this is without parameter sharing, this is with parameter sharing. Because that's a general case, but for example, in some applications, maybe they want to train their model over MNIST, and they see that parameter sharing is much better when they have trained their model over MNIST. I think we have result of MNIST for this model. Okay. This is related to your case. This is just the mathematical formulation for the weight sharing. You see that the hidden representation for the second one is W2 times x less than 2, and the W2 is just one column vector W1, and the x less than 2 is just one element from your sequence x1 plus a bias term C, bias vector C, and H3, just one column is added to the previous matrix you have. So it is W1 and W2, and here you have two elements because you are talking about the third element in your sequence. You have access to both one and the first and second element. And again, the bias is C, and until the end that you have your complete matrix. And this matrix is a complete matrix. It means that it has the weight needed for all other previous hidden representations. Okay? So to simplify the notation, I can talk about this notation. It means that the hidden representation for the D sequence is the sigmoid, or sigmoid can be any other nonlinearity. It is not limited to sigmoid. It is the nonlinearity over this W less than D. This column means that all the column. It's our notation from the start of the semester that this means that the whole column, and this means that this is the whole column, and this is the index less than D. All the index less than D, and you can see here that, for example, for the second you have less than 2, just one. And also the sharing of the bias. Okay. And the number of parameters for NADE is here. Maybe just to have a comparison with fully visible sigmoid belief networks. If you do not share the weights, you will see that you have much more parameters. And the generation. Can you think of generation using NADE? I do not have any figure about the generation because it is completely similar to generation using fully visible sigmoid belief network. Do you have any idea about how I can generate if I have access to this model, to this NADE model? What do I need? I have access to the model. It means that I have W complete, and I have the bias, and I have a complete set of V2, B2, V3, V3 until V D and BD. All of them are given to you, assume. How you can generate samples? Yes.
I think it's the same, but when you generate your whatever is the D minus 1 term, you have to pass it and get it first.
Yeah. For the first element, everything is similar. Because for the first element, we just need V1, go through, for example, summation part, and go through a sigmoid, and then generate lambda 1. This lambda 1 is the parameter for a Bernoulli distribution, x1 given lambda 1. Then you can generate from this distribution and call it x bar 1. Everything is similar. What happened for the second one?
So you have to take in x bar, but you'll have to multiply it by your respective term from H.
No, I assume that I want to generate H2. How is H2 generated? Because first I should generate H2, then I should generate a lambda 2. Lambda 2 is generated based on H2. We know that previously that lambda 2 is easily V2 transpose H2 plus V2. Okay? This is similar to fully visible belief sigmoid network. How I can generate H2?
From the first two, take the first two columns from the weight.
They take exactly the first column because it just needs one column here. H2 is W1 times X bar 1. W1 is the first column here. X bar 1, what we generated previously. I multiply them together and add exactly add C vector. C is also vector, and those all together is of the dimension dh, and it's generate H2, and H2 is times V2 plus a scalar generate lambda 2. If you have lambda 2 again, Bernoulli of x2 given lambda 2, you can generate x bar 2. Okay? And I can continue this procedure until the end. I have all the samples generated. Any question? Yes?
That is sigmoid, right?
Sigmoid, yes. I make a problem, yeah. This is sigmoid. Exactly. Thank you very much. It cannot be any number. It should be between 0 and 1. Any question? Okay. So we can easily generate samples from fully visible sigmoid belief networks, similar to fully visible. We can generate samples from NADE. And these are the samples generated using NADE. They may be to some extent not very understandable or not very high quality, but they are the first step toward generative modeling. These are, I assume that I give this to NADE, and then train the NADE. We see how we can train it, and then start to generate samples using this procedure from NADE. These are all the samples. But one more interesting parameters instead of the generated samples to watch is the possibilities or the probabilities, let's say. Because for any pixel, assume this is the MNIST. For any pixel, before generating the pixel, I calculate a lambda value, you know? instead of looking to the pixel itself, if I look at lambda value, what would be this image? This is the probability of, for example, being 0 or 1. Assume that maybe, I do not know, assume that if it is 1, it is black, maybe. Excuse me, white. And if it is 0, it is black. If with one something, assume that I scan it in this way, lambda 2, lambda 3, until lambda 9. Instead of generated sample itself, if I look at this image, how is this image? Is this a grayscale? Is this a binary? Yeah, to some extent grayscale, but this also it has infinite accuracy if we do not have any limitation, because this is the output of a sigmoid, and it can be any number between 0 and 1. It is not even grayscale, because grayscale has some limitation. So if I look at this image, it is a grayscale image, as you said. And these are those images. This part, you cannot maybe discriminate between this and this, but here it is clear that the samples are binary, but here the samples are not binary. They are corresponding, you know? This one and this one. Look at them together. These are the probabilities, and then you sample from those probabilities, you have this image. It means that when the probability is near 1, it is more probable to generate a white pixel, and if it is near 0, it is more probable to generate a black pixel. It is to some extent some types of binary thresholding a grayscale image. It is not exactly that way, because it is sampling, but you can see it in that way. And you can see that even you see some grayscale image. I should emphasize that this is not your generated samples. The generated samples are here. This is just the probability of the Bernoulli random variables, because you are working on a BM list, binary list. Yes?
In the second case, the lambda 2s will be depending on the previous lambda.
Yes. They are calculated. You see, you do not generate these samples all together and then this. When you generate lambda 1, you sample from it and then you generate lambda 2. Yes. It means that you cannot first completely generate this and then sample from the total, pixel by pixel. Yes. Yes. Okay. Any question? Let's extend the concept of NADE into a real, into continuous random variables. Till now, we just talked about binary, or at the start of this session, we talked about categorical distributions, categorical random variables, random vectors. What happened if I am, if my inputs are from a, this is from a, is a continuous random vector. What happens here? What do you think? Instead of random variable, instead of discrete or, for example, binary, you have a complete, if we have a continuous random variable, what happened, do you think? Chain rule is always chain rule. Nothing happened to chain rule. Chain rule is always chain rule. So we can talk about chain rule. Chain rule is again as before. So to model this distribution, first you should select a family. So because x1 is now a continuous random variable, you should select one family from the continuous board and select it. And then the parameter of the model are the parameter for that family. You know, assume that I select the normal or Gaussian random variable to model x1. So it means that the distribution over x1 is a normal random variable x1 given with these parameters, the mu1 and exponent of s1. The exponent is just added to make sure that the result is positive. It is not something important. Like the sigmoid, for example, your variable goes through sigmoid to be between 0 and 1. Here your variable goes through an exponent to be positive, because this is a variance. Okay? So you have, how many parameters do you add to your model? 2 parameters. I have mu1 and s1. These are the new parameters you have. And you go exactly similar to the discrete word. For the xd, oh, it's better to write it here p theta. It is different, but assume that there I write this notation. What happened? Exactly similar to the discrete word. First, you should generate these are parameters. This is your condition given. I make circle and this box because they are different. Given all of them, I can generate a hidden representation named HD. You know how. You multiply, for example, if it is XD, I have this notation. This is how, and a nonlinearity. This is how HD is generated. Okay? And then, using that HD, I generate the mean and the variance. Exactly similar. Previously, you generate the parameter for your distribution. Here also, we generate the parameter for our distribution. Just the distribution is changed. Previously, because you were in the discrete word, you use Bernoulli, you use categorical. Here, you use just normal. Okay? And you can see much more interesting things in that reference. You can see even a mixture of Gaussian there, which is very flexible and interesting to work with. So I think we have the MADE. MADE is not, we do not have enough time to talk about MADE. Just talk about how you can generate samples or density estimate for a continuous word. What do you think? Assume that you are given all the parameters for generative modeling using real NADE. It means that you have W, C, and also you pay attention that there are some more parameters here. You have V, VD, and UD. It is logical because you are two different, because you are generating two different parameters. This is for mean, this is for variance, so you have two different vectors. So I have V2, U2, the bias are also changed, B2 and B2. These are used for the second, and until the end you have VD, you have UD, you have BD, and you have DD. All of them are given to you, and now you want, first assume that we want to calculate the density. You know that we want to calculate a PDF value. It is different from the probability. We know that if you are in the continuous word, the value of PDF in a point is not corresponding to the probability of that point, because isolated points have zero probability in the continuous word. But we want to know that what is the value of our PDF in a point, in a given point. That's here the density estimation. So what can we do? What? How? How I can, you are given this vector x1 till xd. It is given to you and ask you to say how, what is the value of PDF in this vector. You are given a model, you are given a data point, and you are asked to say, you are asked what is this value. How can I calculate it? Step by step, we should calculate each factor because it is based on chain rule. What is the probability of x1? I have the model. You know, if I have the model, I can form this normal distribution, you know, because I have mu, I have S. And I can say that what is the probability of, what is the PDF in this x1 point, you know? Assume they give you a normal distribution. They say that the x1 is distributed as given I should add them to here too, sorry. These are also the given parameters because it is the model parameters. Any model parameters is given to you. If you put x1, which is given to you, in the formulation of the PDF with these parameters, you can estimate the PDF of this point. It is a number. We do not know anything, but it is a number, not important. So the second, we know that if x1 is this value, you can say that what is the distribution over x2. Here you can calculate it. Assume that I call the result of this term mu2. Mu2 is not a parameter, it is the result of that term. And also, I call the result of this term as 2. You know, we can calculate this and this. Why? Because we have access both to the model and the input. So it is exponent of S2. Okay? And you know that this is dependent on x1 because you're conditioning on x1. And this is also dependent on x1. That's important, you know that because it is an autoregressive model. This generates the second number. Until the end, you generate the xd given mu d of x less than d and exponent of sd, which is a function of x less than d. And if you multiply them together, you reach the point you want, which is the probability of that data point, which is the PDF value in that point, your model PDF in that point. Okay, the time is finished. Thank you very much. If you have any question, you can ask.